Hello, welcome to the second part of examples on dry friction problems. Make sure to watch the previous video and previous examples that I did on dry friction before watching this one. Okay, let's look at this example. A recording tape passes over the 20mm radius drive drum B and under the idler drum C. I'll get back to that, so I want to just mark that. Knowing that the coefficient of friction between tape and the drum and drums are this much and this much. Drum C is free to rotate. I already know that. Find the smallest allowable value of P if a slipping of the tape on the drum is not to occur. So again, we are looking for minimum value of P that puts it at impending motion. So this problem, as you can see, is giving us this equation, which is the equation of equilibrium, or sorry, equation of friction on tapes such as this one, belts, and ropes. And I'm going to explain what those terms are and how to use this equation. All right, so our main focus is going to be drum B. And if I want to write something like a free body diagram, is going to be having a moment. I can put it on the drum, doesn't matter. Having a moment of 30 or 0.3 Newton meters. Okay. It has a TA pointing down, and it has another tension pointing down. And look, that's where the idler comes to help us. This is a free rotating. So remember, when we had a rope and a pulley system and it was frictionless up to this point, we always said, hey, it's the same rope, it's the same tape, the tension all across it is the same. So all the way up to this point, P is the same. After this point, it's going to change. And why is it going to change? Because there is a friction on the belt going this way, and it's causing that P not to be equal to TA. If this was frictionless, if B was frictionless, then I can just say this is P, this should be P, because this is the same tape going around. But now the friction has messed up that equilibrium, so it's not P any more. Okay, let's see. Let's write summation of moment about center. Summation of moment about point B, this way being positive. I have a TA multiplied by R. Do I have the R? Yes. 20 millimeter radius. Let's just write it R. Minus PR minus M equals 0. So I can have, let's rearrange this, radius, which is 0.02 meters, and TA minus P should equal the moment, 0.3 Newton meters. Therefore, TA minus P, I'm getting 0.3 over 0.2 Newton meters. I get 15 newtons. Okay. The difference between those two is 15 newtons. And that is caused by what? That is caused by the friction. Again, up to this point, all the ropes, pulley system, tapes, belts, everything that we have had was frictionless. P or T or whatever you want to call it was the same. But now you can see the difference between them is a 15 Newton, and that's because it's not frictionless anymore. So now we got to use this equation. And this equation, you can definitely look in the book and see how it was derived and what goes into it and why this equation is governing equation for friction on tapes and belts. But what I tell you is how to use it and how to plug numbers in it and use it easy. E in this equation is just the base of natural logarithm. So it's base of natural logarithm. This beta is called contact angle, or is the angle of belt, or in this case tape, to surface contact, and it needs to be in radians. Okay, and that means how much this belt and that surface are in contact. What is the angle? In this case, the angle is here, so let me draw it a little bit better. The tape is contacting the drum this much. This angle here, which is 180 degrees, and the way to convert those together is 1 degree over 360 degrees equals whatever radians that you're looking for over 2 pi. So if I put it 180 here, I'm going to get a contact angle of pi. All right, so that's how much the contact is between the belt and this drum, pi. So now let's go insert it into that equation. In this case, T2 is this one. T2 is the one that is resisting friction. P is just like T1. So let's insert it into that equation. T2, which is TA, equals T1, which is in this case P, E, mu, which we have is 0.4, and beta, which is pi. And that's it. So let's see, TA, I can replace it. TA equals P plus 15 Newton. So 15 plus P newtons equals P E 0.4 pi. The only unknown here is P, and it will result in P of being 597 newtons. Okay. E, by the way, if you're looking for the value of E, is 2.7182. But usually when you put it in your calculator, almost all calculators, they have the value already in them. All right, let's look at another one. And again, the problems that involve friction, a rope or belt like that, it's just really easy to use this equation. You only have to figure out the angle and which force is what. Let's look at this problem. A rope having a weight per unit length of this much is wound 2.5 times, that's important for us, around the horizontal rod, knowing that the coefficient of static friction is this much, mu. Find the minimum length of X rope that should be left hanging if a 100-pound load is to be supported. All right, so let's see. I have a cylinder. I have a tension 1 going this way. T2 in this equation is always the one that is fighting friction. So it's T2 is basically T1 plus force of friction on the rope. Okay. T2 is easy. T2 is 10 feet of rope which has this much weight plus 100 pounds. Okay. And this is going to be 104 pounds total. So the weight plus this much rope that is hanging. T1, on the other hand, is X feet of rope, and how much weight it is? 0.4 pound per feet. So it's 0.4x pound. Okay, mu is given 0.3. The only thing left to find is beta. Beta is how much contact is between the rope and cylinder. It is wound 2.5 times. So it's 1 time which is 2 pi. The second time, which is another 2 pi, and a half time, which is pi. So that is 5 pi. In other words, 2.5 times full circle, which is a 2 pi, 5 pi. So I think we have everything that we need. Let's insert it in that equation. So I have 104 pounds equal T1, 0.4x e to the power of mu, which is 0.3, multiplied by 5 pi. All right, this equation, only unknown is x, and it should result in 2.34 feet. Again, once you understand what those terms are and what is beta, everything else is really easy for problems like this one. Okay, let's see. 2 blocks A and B have a weight of 10 pounds and 6 pounds respectively. They are resting on the incline for which the coefficient of static friction are this much and this much. Find the angle theta which will cause motion of one of the blocks. What is the friction force under each block when this occurs? Okay, doesn't say which block, but it's going to increase theta until one of them slips. Okay, let's see. The first thing I do is draw a free body diagram of each of them. Let me draw them here. A has a weight angle theta, has a normal force, and if we want to start sliding down, the motion is going to be this way, so the friction needs to go opposite, and I call that FA. And the only other thing attached to it is just F of a spring. Okay. Block B is like this one, has normal force B. If it starts going down, same way, motion being down, friction of B is going to go up the ramp. It has a weight of 10 pounds, and it is attached to force of a spring. All right, that's our free body diagram. Okay, let's see. So none of the blocks moving yet. So what does that mean? That means this spring is not stretched or compressed yet. So if a spring is not compressed or stretched, what does that mean? That means the force of a spring is 0. Okay, that made life much easier. So problems, I told you to have x and y rotated a little bit. Summation of forces in x being 0, Fa minus 10 sine theta being 0. Summation of forces in y being 0, Na minus 10 cosine theta being 0. From the second free body diagram, I can write same thing, Fb minus 6 sine theta being 0, and Nb minus 6 cosine theta being 0. Okay. So now I have to decide which one moves. Let's make an assumption. We're going to go the route of making an assumption. So assume A will be in pending motion. Okay. The reason I'm asking that is the reason I'm assuming is I'm looking here. I see less coefficient of friction at A. So I'm assuming A will start slipping first because, you know, they have the same weight and everything. And then I can check the assumption to make sure it's correct. If A is in pending motion, then I can say this one is 0.1 NA. Yeah, and that's it. So then from here, I have NA of 9.889. I get theta of 8.531. I get FA of 1.48. I get FB of 8900 pound. I get NB of 5934 pounds. So just one assumption helped me solve this problem. But I don't know if that's correct or not. Okay. One way is to then assume B is in pending motion, not A. So then you cannot use this equation. Instead, you have to use 2.5 NB. And I've done the math. The angle that I get is going to be 14,036. So let's see what that means. I start from theta of 0 and I increase the slope. When I reach 8.5, what happens? A starts to slipping. The problem says find the theta will cause motion of one of the blocks. So I'm done. So that means theta is the angle, this one is the angle that will cause motion, and it will cause motion in A. Because B requires a lot larger angle, then it starts moving and it starts motion. But also another way is to check your assumption. So remember, you can do two ways. First, assume A, solve it. Assume B, solve it. Compare the angles, compare the forces, whichever is problem asking for, and figure out which one is correct. Or assume A and just check your assumption. And this is how you can check assumption A to see if it's correct. Check to see if my assumption, let me write it here. So assume A moves first. .15 NA, and I got those value. The one that I really interested is FB that I got 899 pounds. To check it, To check, I'm going to find FB if B slips. Okay, and that will be the maximum B would be MB normal force B. That's going to be 0.255934. That is pounds, which will be 1.483 pounds. So A slips first. What FB do I get? This much. B slips first. This is the FB I get. So FB, so block B does not slip. Therefore, my assumption was correct. And the value that I'm looking for is the theta of 8.53. Okay, let's look at another problem. Find the maximum horizontal force P that can be applied to 12 kilogram hoop without causing it to rotate. Let me really quick go back to make sure that maximum and minimum, everyone understand it. Friction. I start from 0, I increase the force P, I reach this point. This is the maximum force that I can apply without causing it to rotate. Why? Because this is impending motion. Nothing is moving. Okay, so it all points to the same point of impending motion. I just don't want you to get confused about when it says minimum, maximum. So it all points out to that point. Okay. And we have coefficient of friction and we have R. Okay. First is to draw free body diagram. Active force, which is P, that we want to find. The other active force acting is the weight. I put it in the center. 12 kilograms, so it's going to be 9.81 newtons. And then go put reactive forces. Point B has a normal force. Point A has a normal force. And if I apply force P, it is going to cause an impending motion of this way. So friction on both of surfaces is going to be opposite that direction. So I'm going to have a friction at point B and a friction at point A like that. Okay, that's basically the challenging part about this problem. Everything else is just really simple. You write summation of forces in x equals 0. I have P plus FA minus NB equals 0. Summation of forces in y being 0. So I have NA minus 12, 9.81 plus FB being 0. What else I can write? I can write summation of moment about point A being 0, this point. So W, FA, NA, they all go through it. No worries with any of those. I have an FB of 0.3 meters. I have an NB of 0.3 meters. I have a P of 0.6 meters equals 0. The two equations that I can use, Once the ring starts moves, or impending motion, I can say FA equal 0.2 NA and FB equal 0.2 NB. So 0.2 NB, 0.2 NB, 0.2 NA. And this, I have three unknowns, three equations now. I should be able to solve all of them. NB results in 53.51. NA will be 107.2. FA will be 21.40. FB will be 10.7. And the most important one that I was after is going to be 32.1 Newton. That's the maximum force, and this point is right there, 32.1 Newton. That's the maximum force that I can apply, and without this ring or hoop, as it says, without causing it to slip. Okay, let's look at another problem. Friction pawl is pinned at A and rests against the wheel at B. Wheel pawl. It allows freedom of movement when the wheel is rotating counterclockwise above C. Clockwise rotation is prevented due to friction of the pawl, which tends to bind the wheel. Determine the design angle which will prevent clockwise motion for any value of applied moment. This is a very interesting problem. So let's see. There are two ways that you can solve this problem. One is to use free body diagram of the wheel, okay, which I have it here. So something like that, like this. Point C, I have a moment. Point C, take it as a pin, CX, CY, and then point to B, which is of interest to me. Going to have friction, going to have a normal force at B. You don't need any equations of equilibrium to solve this problem if you use free body diagram of the wheel. You can use very basic resultant vector addition and solve this problem. Let's see. I'm going to draw it on this figure down here because I need those angles and theta. Okay, I have normal force going this way. I never recommend drawing forces on a diagram. Free body diagram always should be like this because you need the outline and all that stuff. But to understand the angles better here, this is one exception that I'm doing the diagram actually on the point. And there is a friction force FB. So now I'm interested in those angles. The resultant force for these is going to be in this direction. Okay. The angle between NB and vertical line is 20 right here, and this angle is theta, so therefore this angle is theta. So this entire angle is 20 plus theta. So I'm going to draw it here one more time. Well, that's not the best way to draw it. Let me draw it a little bit lower. I have FB NB, and this is the resultant force of those two. And this angle, this entire angle is 20 plus theta. This angle right here, 20 plus theta. So now let's see, impending motion, I have tangent of 20 plus theta equals FB over NB. For impending motion, I can write FB equals do I have the mu, or is the mu not given? Okay, I think that the mu should have been somewhere, but it's a typo. So take mu as 0.6. All right, there we go. All right, now I have this. So tangent theta plus 20 now equals 0.6 NB over NB. So theta will be 110 degrees from there. So with that theta, any value of applied moment will not cause slipping, because you see that my solution didn't depend on theta at all. The second solution that you can do is draw a free body diagram of the pawl. Okay, the solution number 2 is FBD of pawl. Again, I drew it here because I need those angles to go over. So for the pawl, something like that, I have AX and AY, that's a pin. So I'm just going to put AX, AY. And then point B being here, I have friction, and I have NB for the pawl. For this one, if I write summation of moment about A being 0, I can find the relation between, I can find the angle theta. But let me add a little bit of explanation here based on the diagram that I have for pawl. So this FB, this angle being theta, NB having this angle right there, FB being there, the line of action of FB, if it makes a 90-degree angles, because this line is perpendicular, or sorry, parallel to this line, because remember, F and N are perpendicular. N, F, there's 90 degrees. So this line that makes an angle of 20 right here will make an angle of 20 right there when it's perpendicular. Okay, that's all I wanted to show on this diagram, that is 20 degrees. So now let's see. If this length is whatever, I don't care, L, this is 20, this is theta. Now I think I can write equation of moment about point A. I have AX and AY, they go through it, I don't care. this length is going to be L cosine theta plus 20. Okay. And this length is going to be L sine theta plus 20. So the summation of moments, I have FB L cosine theta plus 20 should be equal to, or if I want to go based on my sign, is NB L sine theta plus 20 equals 0. I'm sure by now you all know what I'm going for here. It is similar to the other one. L is irrelevant. Therefore, tangent theta plus 20 is FB over NB. Look, I got the same thing. So if you go based on the wheel or based on the cam or the pawl, you can solve it. This one, I didn't even need to write equations of equilibrium. It was just a resultant force, triangle, and trig. This one was actually a summation of moments about point A. So from here also you get theta of 110 degrees.